Welcome to the fascinating world of Prolog, a programming language renowned for its logic and elegance. At the heart of Prolog lies the concept of unification, a fundamental mechanism that drives its reasoning capabilities. Unification is like a puzzle solver attempting to match Prolog terms together. It's the process of determining whether two terms can be made identical by assigning values to variables. Imagine you have two pieces of a jigsaw puzzle. Unification is like trying to fit those pieces together. If they match perfectly, we have a successful unification. This process is crucial for Prolog to answer queries and deduce information from facts and rules. Unification doesn't simply check for equality, it's more sophisticated. It can handle variables, allowing for flexible and powerful pattern matching. For instance, if we have a variable x, unification can try to find a value for x that makes two terms identical. In essence, unification acts as the backbone of Prolog's inference engine. By understanding unification, we unlock the true potential of logic programming and its ability to solve complex problems through deduction. Let's delve into the specific rules of unification and explore its workings through illustrative examples. Unification in Prolog follows a set of well-defined rules. Let's start with the simplest cases: constants and variables. Constants are like the atoms of Prolog, representing fixed values. They can be numbers like 1, 2, 3, or atoms like Apple, John, etc. When we try to unify two constants, the rule is straightforward. They unify only if they are identical. For example, 1 unifies with 1, Apple unifies with Apple, but 1 does not unify with Apple. Variables, on the other hand, provide flexibility. A variable can be thought of as an empty box that can hold a value. When we unify a variable with a constant, the variable is instantiated with that constant's value. Think of it as putting the constant into the box. For example, if we unify the variable x with the constant cat, x takes on the value cat. Furthermore, two variables can unify with each other. In this case, they become linked. Any value assigned to one variable is automatically shared by the other. It's like connecting two boxes with a rope. Whatever you put in one box appears in the other. These simple rules form the foundation of unification. Next, we'll explore how unification handles more complex structures, allowing Prolog to represent and reason about relationships between objects. Moving beyond constants and variables, Prolog allows us to represent relationships and complex data through structures. A structure consists of a functor, name, and a sequence of arguments enclosed in parentheses. For example, is a structure with functor loves and two arguments, John and Mary. This structure represents the relationship of love between John and Mary. Unifying structures involves a recursive process. Two structures unify if and only if 1, they have the same functor and the same number of arguments, arity, and 2, their corresponding arguments unify recursively. Let's illustrate this with an example. Consider two structures, and. These structures can unify because they share the same functor date and have 3 arguments each. The unification process then checks the corresponding arguments. 1 unifies with instantiating to 1, January unifies with instantiating to January, and 2025 unifies with instantiating to 2025. Through this recursive process, the two structures unify successfully. However, if we tried to unify with, the unification would fail. This is because the structures have a different number of arguments, violating the first rule of structure unification. Understanding structure unification is crucial for working with complex data representations in Prolog and leveraging its full power for knowledge representation and reasoning. Section 4. The power of Prolog's equal sign operator. In Prolog, the equal sign operator is more than assignment. It tests and establishes unification between terms. Instead of assigning values, it checks if terms can be unified. If they can, Prolog says yes and instantiates variables. Combining equal sign with backtracking reveals its true power. Prolog explores facts and rules to find solutions. The equal sign operator with unification expresses complex relationships. Prolog finds solutions showcasing logic programming's power. Section 5 occurs. Check and infinite terms. While unification is a powerful mechanism, there's a subtle but important aspect to consider, the occurs check. This check prevents Prolog from falling into the trap of infinite terms. Imagine we try to unify the variable x with the term. This means x should be equal to a structure that contains x itself as an argument. This creates a circular dependency, leading to an infinite term, going on forever. The occurs check is a safety net that detects such situations. If unification would lead to an infinite term, Prolog throws an error, preventing endless recursion and potential system crashes. However, the occurs check comes with a cost. It adds complexity to the unification process and can sometimes slow down Prolog's execution. As a result, some Prolog implementations choose to omit the occurs check for performance reasons. While omitting the occurs check might offer speed improvements, it's crucial to be aware of the potential risks. Infinite terms can lead to non-termination and unexpected behavior in Prolog programs. Therefore, understanding the occurs check and its implications is vital for writing robust and reliable Prolog code, especially when dealing with recursive data structures or complex unification scenarios. Section 6. Prolog's Proof Search, Navigating the Search Space. Prolog uses depth-first search with backtracking to answer queries. Imagine Prolog exploring a maze, each path a potential solution. It starts by finding a fact or rule that matches the query. This is like finding the maze entrance. Prolog then solves sub-goals, stepping deeper into the maze. If it hits a dead end, it backtracks. Backtracking means trying a different path. This systematic search finds solutions or exhausts possibilities. Let's illustrate with an example. Suppose we have the facts: parent, John, Mary. Parent, John, Peter. Parent, Peter, Alice. Querying Prolog returns the matching fact. Asking for more solutions makes Prolog backtrack to find another match. This strategy efficiently explores possible solutions, making Prolog powerful for AI, natural language processing, and expert systems. Section 7. Practice Exercises. 1. Unification Challenge. Determine whether the following pairs of terms unify. If they do, specify the variable instantiations, A and B, and C and D, and 2 family tree queries. Consider the following Prolog facts representing family relationships: parent John Mary, parent John Peter, parent Peter Alice, parent Anne Mary, female Alice, female Anne, male John, male Peter. Write Prolog queries to find A. All the children of John, B. All the grandchildren of John, C. All the siblings having at least one parent in common, D. All the aunts of Alice, female siblings of a parent. 3. List manipulation. Prolog represents lists using square brackets. For example, represents a list with elements A, B, and C. Write Prolog predicates to A. Check if an element is a member of a list, B. Append 2 lists together, C. Reverse a list. These exercises provide a starting point to test your understanding of unification and Prolog's proof search mechanism. As you explore more complex problems, you'll gain a deeper appreciation for the power and elegance of logic programming with Prolog.